Hello fans of GeoGebra. We have a new problem once again. It's more complicated in real life, but it's not more complicated with the Muller Breslau method. So we have a beam that's inclined. It has a lateral load and a vertical load. It's pinned at the right edge, which is up above. It's a slanted beam, and it's completely fixed at the left end. So it's 2 times indeterminate. The process is the exact same as it was for the previous example. There's only one slight difference, and it's really not hard at all. So I'll show you what's happening here. In the previous problem, we had pinned, so this perturbed beam was a straight beam. Now it's not a straight beam because I have to respect all of the other boundary conditions here. So the slope must be the original slope. How do you do that in GeoGebra? Really easy. I just put a point anywhere on this slope, but it really doesn't matter too much. I just put it really close to this edge here, and now I have 3 points, 1, 2, 3, and that point over here is what I'm calling mover. So let me explain how I did this. And this is a circumcircular arc, just as Leonhard Euler and the Bernoulli brothers did. Circumcircular arc. 1, 2, 3. Those guys use GeoGebra also, I think. Okay, so how do we do this? It's a combination of 2 things. General plane motion is a combination of 2 things. Rigid body rotation and then this translation. So the rotation is just as we saw before. We have the blue beams spinning around this axis point, not changing length. And the perturbation is the vertical change here. That's the thing that I'm looking for. Since I'm looking for the vertical reaction, I need the vertical perturbation. But you could see now with mover that I have not respected the second boundary condition. So all I do is respect that second boundary condition. I put mover over here, and I run that circumcircular arc 1, 2, 3, and I look where the load was to where the load is. And the loft L perturbed is this, L for lateral, the loft G for gravity perturbed is this. Super easy. The only slightly tricky thing, I think, is that you do need to respect where that load is. And what I did was I just said it's 2/3 of this stretched beam. So 2/3 of that stretched beam, you could see right there, that load follows on this arc, which is 2/3 of this beam, the stretched beam, instead of 2/3 of the circumcircular arc. So that seems perfectly reasonable to me. So then the work of the lateral load is the force times the loft L perturbed. The work of the gravity load is the force times loft G perturbed. You divide by the perturbation. I did this in SAP, for just a standard beam that SAP gives us. 624 is the reaction upwards on the right. And here we go. Let's do our virtual work Muller Breslau perturbation. And I got 651, 642, 633, 631 or so. So that's about as low as I get. And I don't have that flip. I'll have to think about that. But that's pretty spectacular. Also, ladies and gentlemen, it doesn't matter how complicated the loads are. I have point loads here, but if I had distributed loads, I would just take the equivalent load at the centroid of that distribution and track how it moves. Even if I had 2 different types of loads on this beam, which I'll do in the next video. All right. Thank you.